Hi, my name is Tom Webb. I'm a postdoc at the University of York studying the coastal cryosphere. I'd like to welcome you to the Cryosphere Pavilion, where we're presenting this talk on future A to B images and maps you can't unsee. And I'd like to welcome those as well joining us at hubs in Geneva and Stockholm. If you have any questions, feel free to ask. That is either in the chat or your host directly, and during the question and answer session at the end. And now I'd like to introduce our first speaker, Karen Floridi, who is Vice President of the Climate Central.
Thanks so much. It's really a pleasure to be here and speak to you today about our maps and images. This is going to be a presentation in two parts. I'm going to do the first part, and then my CEO and Chief Scientist, Ben Strauss, will be joining us to do the second part. The first part that I'm going to be doing is focusing on... it's not advancing. It was advancing a moment ago. There we go. I'm going to be talking about our Climate Matters program. This is something that we set up about a dozen years ago to start helping meteorologists, particularly TV meteorologists and weathercasters, communicate with their audiences on a range of topics that involve the weather and climate connection. It's been a very effective and successful program. We now have nearly half of the TV meteorologists in the United States are participating in it. And from time to, so this is what it looks like on the air. Every week we're producing a bulletin for meteorologists to put on their green screen, also for increasingly for non-meteorologist journalists on all beats, all media. They use it on the air, they use it in print digital, they use it on social media. And our particular niche as an organization is using data-rich information to produce highly localized visuals. Now, we do a fair amount of work, or some amount of work, involving the cryosphere, which isn't as readily localized as a lot of our other topics. But I want to show you quickly what the materials that we are using in the cryosphere, or producing in the cryosphere, look like. And by the way, we do this, I mentioned we do weekly bulletins. We do them simultaneously in Spanish as well as English, and we put them all up on our website for everyone in the world to see. Although most of our subscriptions are free, most of them are in the media. Anyone is welcome to sign up who's interested in receiving it. So a couple years ago, we typically every year when we get to the sea ice minimum, we are doing something that relates to that. So this is kind of a fairly core version of it that we did a couple of years ago. Really just trying to make immediately visual to the viewer what the information is. Another year we did the age of Arctic sea ice, showing that a lot of the ice is a lot younger than it used to be. And then we have materials that go, it's not just the visual, as I'll mention a little bit later, it's also things that go along with that. A couple years ago, actually in 2015, we took the occasion to focus on the 100th anniversary of an ice classic, which relates to when does the river ice thaw enough to break. And as you see, that date has gotten earlier and earlier, meaning spring is coming sooner and sooner. This is one that we actually animated. Even earlier than that, we had done a basic explainer saying, here's what happens when the heat spirals in. And then we've been able to use this repeatedly in the coming years. Also using this, the opportunity to talk about the ocean, the global conveyor belt in the oceans. And how those specifically relate to the cryosphere. Sometimes we go for a more humorous kind of treatment, as Santa getting really hot under the collar. And then one of my personal favorites is what we did a couple of years ago when one of the big, when the Larsen ice sheet calved and made a very, very large iceberg So we wanted to convey just what the volume of that was, because it's hard to get your head around. So we made a great ball of ice, and that's what it looked like. And we also did this for a number of other cities, including and locations, including America's most iconic national park, the Grand Canyon. So that's a great ball of ice in the Grand Canyon. Just to briefly mention that we do a lot of work that goes way beyond the cryosphere. So more typically, we're talking about things involving weather, like less extreme cold. This is a series that we just did last week for about 250 locations, again, throughout the United States, that are looking at what is the local impact of whether we get to 1.5 versus 3 degrees. In the summer, we're typically talking about heat in any of a dozen or so different ways. We'll also talk about deluges and droughts and things that result from those kinds of impacts, like decline in corn and other foodstuffs, decline in wine, things that really catch people's attention, more air pollution, more icky bugs. And when we do these, it's not just the visual. It's embedded in a short bulletin that contains usually additional explainer graphics, as well as key concepts and experts to interview and so forth. So that's the quick overview of climate matters in the cryosphere. And now it is my pleasure to introduce my colleague and my boss, Dr. Benjamin Strauss, who is the chief scientist and the CEO of Climate Central. Before I do that, let me see if there are any quick questions, or not so quick questions, on the Climate Matters materials. Okay, if not, we'll turn it over to Ben.
Thanks, Karen. Can you hear me all right? Yeah, okay, good. And here we are, part 2. So I'm going to share a bunch of imagery about different futures that we could create depending on whether we warm the planet by 1.5 degrees Celsius or 3 degrees Celsius, or some other increments in between and above. These are long-term projections. So to be clear, what I'm about to show, it's not happening this century, but we make the choice this decade or the coming few decades, right? Because that sets us on the path to 1.5, 2, or 3. This defines the legacy that we leave, really how the future remembers us and what we left behind for them. So this imagery, some of it is in a Google Earth environment. That's what you're looking at right now. Some of it is going to be photographs that we then altered in Photoshop. But all of the water levels are based on peer-reviewed scientific projections, closely related to all of the talks that have been going on here in the pavilion over the last couple days on the future of the ice sheets and their response to warming. So here we're looking, we'll start in Buckingham Palace since we're here in the UK. And this image shows how it looks today with the present day sea level. And the next slide I'm going to show is the projected sea level from the warming that we have already experienced through today, right? Because ice takes time to melt, and the Antarctic and Greenland ice sheets haven't yet caught up to the amount of warming that we've caused, just as if you walked down a long bank of freezers filled with ice and you unplugged every one, the ice wouldn't melt and spill out instantly. It would take some time to melt and the seas to rise. So here in the next slide, we show about 5 feet of sea level rise that's baked in. And if you look closely, you'll see in the corners a little bit of salt water creeping in. So that's unavoidable sea level rise already baked in. If we go back, that's today. And there's the unavoidable sea level rise. And now we move to 1.5 degrees next for Buckingham Palace. Now, everything that I'm showing you here today is all available on our website at picturingourfuture.org. We actually have about 1,000 images. I'm showing you some of the highlights, but they're for about 200 locations and 100 cities around the world, and the maps cover the global coast, at least between the latitudes of south of New Zealand to Iceland or so. So now we're going to move from 1.1 to 1.5, and things look a lot worse. That's the target here, 1.5 degrees Celsius, right? But if we slip to the older target at 2 degrees, that's 2 degrees. Turns out that the difference between 1.5 and 2 degrees is probably the most consequential half degree in all the degrees north of 1.5. I mean, they all matter a lot, but the biggest difference in terms of sea level rise and the amount of buildings, kind of cultural iconic sites, development, population that would be affected, the biggest difference is between 1.5 and 2, according to our current analysis. And that's because there's a lot of sea level rise from that increment, and also because just as a species, we have concentrated our cities, our development at the lowest elevations above the high tide line. So the first few meters of sea level rise are going to be much more damaging than the next few meters after that. All right, so now we move from 2 degrees up to 3, and now up to 4. So we really don't want to go to any of those places. I should say that this made a little bit of a sensation in the UK press. We published it in connection with a scientific paper, got a lot of coverage. And one of the tabloids came out and said it was all wrong because Buckingham Palace is 17 meters above sea level. And I'm afraid they got their units wrong. It's more like 17 feet. Okay, we also have a resource next to all of these images, which is a map that's, in fact, considerably more comprehensive than the images. And you can really see the spatial extent. And the map, like the images in Google Earth, is very flexible. So here we're comparing areas affected by the multi-century sea level rise after 1.1 degrees of warming, or what we've already locked in, versus 1.5 degree, the target. And the difference is the yellow, right? The purple area is what is already baked in. The yellow is what we add when we move from 1.1 to 1.5. And now we're going to move the sliders. All of this, again, is available via that picturingourfuture.org. Let's move the slider. And now we're going to compare 1.5 versus 2. In a way, the colors kind of flip, but everything in purple is now what's affected at 1.5 degrees. And the yellow shows the difference between 1.5 and 2, the extra area that would be affected if you go up to 2 degrees. So that's right, London is in the bullseye of this, and the Thames barrier is not up to this, not close to design for anything like this. I expect that in a future like this, that a much more substantial barrier will be engineered, or major levees will be built along the Thames estuary with a lot of disruption, cost, and other difficulties. Now that's 1.5 versus 3, and up to 1.5 versus 4. So this map lets you explore 1/10 of a degree at a time, all of the different potential future locked-in sea levels, depending on where we end up with our targets. And so we really offer this as a tool to you here and to the world as a way to really visualize the stakes, the long-term stakes that we're talking about for different cities and countries and communities. Coming a little close to home, this is where we are right now, the SEC Center. I guess that's the OVO hydro, so we're probably somewhere out there, a little wet. That's 3 degrees. So that's the 3 degree scenario. I'm going to go backwards now. What would happen if we limited warming to just 1.5? Well, we'd still be wet, but the ovo hydro would be better. Okay. I'm going to show a whole bunch more images, but before I do that, I'm going to show a 2-minute video, which is a really, colleagues did this. It's really striking. It's a little bit of a world tour with motion, right, of this difference between 3 degrees and 1.5 degrees. Just 2 minutes. So here we go. So I think it is a heavy burden to understand that what we do for the next 10 years will have impacts that last 1,000 years. But it's also a great opportunity. And there is an opportunity for us to have such an enormous influence on the future and our future path. And I don't know that any human generation has actually had that understanding, understood that what they did in a 10, 20, 30-year period would last for hundreds and thousands of years in terms of its implications. And this video and all the images are freely available to use, reuse, distribute. It's up on YouTube. It's on our website. So we're definitely appreciate anyone's help here, continuing to disseminate it to the group that's gathered here in Glasgow. I'd be interested in your impressions when we get to the Q&A. Here's a little bit more. So here we are in Shanghai. 3 degrees. 1.5. Actually more striking for Shanghai. Well, first, here's Guangzhou. This means that the camera is below the water level. The camera position. 1.5 degrees. What's more striking about Shanghai is not any particular image, actually, but to me, it's the map. Here's a map in purple, shows the areas below the high tide line after 1.5 degrees of warming. Yellow is the difference, 1.5 to 3. I mean, look, the whole peninsula is purple. And it's not just Shanghai, it's multiple other cities. I will also point out that Shanghai looks like a little yellow island. Maybe Shanghai could be protected. Well, all of these maps are based on an elevation data set that we developed at Climate Central using machine learning to improve on the elevation data sets made available by NASA and other space agencies. The problem with all of the global elevation data sets we discovered some years ago is that they derive from coarse satellite sensing that could not distinguish between treetops, skyscraper tops, building tops, and the ground. And as a result, the average elevation in the coastal zone was more than 2 meters too high, which is a huge problem if you're trying to understand the effects of, say, 1 meter of sea level rise this century. We're looking at bigger amounts of sea level rise here, but for projections this century, it's more like 1 meter. So we spent years working on new elevation data that would eliminate that bias, and we have been mostly successful. We've gotten it down close to 0 on average, but there are still some places I'm convinced that we have a bias, and I think Shanghai must be one of them. It's why it looks like a yellow island, because all of the high rises, all of the skyscrapers, our machine learning algorithm probably couldn't get 100% of them out of the picture. So I suspect things look even a little bit worse than this for Shanghai, which is a terrible thing, but it also means that, the world's largest emitter of carbon dioxide right now has enormous stakes, just like every country in the world. All of us have great stakes in this choice. Here's a look at Jeddah Tower, which is being built in Saudi Arabia after 3 degrees Celsius. It's halfway done. It is engineered, designed to be the world's first building that's 1 kilometer tall. But being 1 kilometer tall will not help if your toes are in the water. 1.5 degrees Celsius. Here is the world's current tallest building, the Burj Khalifa in Dubai. And all of Dubai after 3 degrees versus 1.5. Here's a look at the map. So you can actually see there's a great deal to be saved by limiting it to 1.5 degrees versus 3 for Dubai. Many places will build defenses. A place like Dubai probably has a better shot at defenses than many other places. Build a thick, fortified levee. You lose the character of a place, but you can probably keep the water out. There are 2 great dangers to levees besides the problem of what might need to be destroyed to make way for them and the loss of character. One is, what if the levee fails, right? How deep of a bowl do you want to live inside of? Hurricane Katrina in New Orleans gave us a little taste of what can happen when you live below sea level and the defenses fail. Water rises very quickly. So that's a situation you really don't want. The other is, what do you do with the rain? How do you get it out? You need a massive system of pumps, and the pumps can never fail, right? They can't go out in a big storm. They have to be totally bomb-proof. Big rainstorm, probably not the biggest concern in Dubai, but if it did happen, if it did on that rare monsoon occasion, right, there's no vegetation to absorb it, right? It's like deserts or dry desert until there's a rainstorm and it's a flash flood. So that actually could be a problem. Anyway, there are possibilities for adaptation, but also limits to it. Nigeria. Here's the central mosque in Lagos, 3 degrees. And now we move 1.5. Here's the map. So Lagos, a lot of Lagos could be spared by limiting to 1.5. Here is the Plaza de la Catedral in Havana. Cameras below the water level. You can see the water makes it above the tops of those umbrellas, but it's all dry in 1.5. The Temple of Literature, 1,000 years old in Hanoi, 3 degrees. 1.5. You know, I'm from the United States, and the Western culture in the United States is relatively young. I mean, we're a few hundred years old. But in Europe and in Asia and in Africa, there's history that is thousands of years old and that we still revere. So we're talking about protecting the culture, that heritage from the past and the heritage that we're creating today so that our descendants can enjoy that. The map for Hanoi is pretty grim here. All this in purple, below 1.5. Hanoi up here is spared if we can limit things to 1.5 and not 3. The map of South Vietnam and the Mekong Delta looks even worse. The Maldives, 3 and 1.5. Here's Dhaka in Bangladesh, 3 and 1.5. We have buttons of showing that too. If anyone wants a button, come find us at the end. And here's a look at the map here, orient myself. So Dhaka, we've got another one of these island effects. I don't know if that's real or perhaps caused by development in the city. Zooming out, there's a picture of Bangladesh on the whole. So a massive area, right? A massive coastal area, which currently has a whole lot of people living there, a lot of rice farming, a lot of wildlife. And in a landscape like this, I don't see how you build levees. You know, there's too much shifting, complexity, sinking. Here's a look at Mumbai. It's not just the Bay of Bengal, but also the west side of India. This is a major museum of Indian history in Mumbai. And here's the map. So a lot to lose, a lot to protect. Here's St. Petersburg in Russia, another top 5 emitter or so. Makes a big difference in St. Petersburg. St. Petersburg is a very interesting map because downtown is almost entirely spared if we limit to 1.5, but it's all underwater after 3. Here's a look at Cape Town, South Africa. 3, 1.5. And here again is the map, even stronger for Cape Town. City is almost entirely spared if we limit to 1.5. Here's Rio de Janeiro, the Copacabana. And to look at the map. Here's a legislative seat of British Columbia in Victoria. If you've never been to Victoria and you have the chance, I used to live in Seattle. It's absolutely beautiful. There's 1.5. And then back to my national home, there's our legislative capital in Washington, D.C., 3 degrees and 1.5. And here's a map. For those familiar with the mall, it could become an island there. All right. So just to, I'm going to wrap up by showing a few more pictures, different time frame. We've got this map. The maps I've been showing are really a multi-century time frame, right? No one's going to drown from that sea level rise. It has to do with the long-term heritage that we can protect or not. But of course, there are coastal floods are being made worse today by sea level rise that has already happened, and will continue to be made worse this century by continuing sea level rise that will depend on our emissions. Here's a look at land projected to be below the tide line by mid-century in Mumbai in red. And all these maps you can see in map view like this or satellite view. So just mainly around the margins or maybe in the park area to the south. But we can change the settings. If I click on change other settings, we're looking at the current pollution pathway, kind of mid-range sea level projection, and sea level rise at the top, just sea level rise. Let's change that to sea level rise plus a typical worst of the year flood. And you see that a much larger area is below that elevation. So we have this whole global map on offer. It's all based on this kind of just published, kind of most advanced in the world coastal elevation data set. So really, this is the best picture that you can get of coastal threats today at a global scale. And it's all the projections here, the latest IPCC projections. The flood levels are based on leading science and modeling of global flood levels. You could do a better job if you did a specific analysis for Mumbai. In this map view, you can choose many different maps. Just to show, I've been showing earlier we were looking at warming choices. Now we're looking at year. And for those with a special interest in Greenland or Antarctica, you can choose ice sheets to see if Greenland or Antarctica contributed 1 or 2 meters, what would that look like globally, including the spatial fingerprint of that sea level rise. Okay, but going back to this map, this session is focused, the cryosphere theme is past 2100, so we can zoom up to 2150. Here's the land below the annual flood level there. Here's the land just below the sea level, the projected high tide line, so that's looking a little better. But we can go in and also change some of the assumptions. Right now we're looking at the main IPCC model, current emissions trajectory, kind of mid-range projection. Now let's change it to the second IPCC model that includes more ice sheet dynamics that we have less scientific confidence about, but are possible and have been discussed at length here in the pavilion yesterday. And let's say we have some bad luck, that those ice sheets turn out to be on the kind of unstable end of the continuum. That 10% chance that Rob DeCanto and Jonathan Bamber were talking about yesterday. So that doesn't look as good for 2150, and this is just land below high tide. Now if we change it to an unchecked higher pollution scenario, that's what you get. You can really unloose the faster sea level rise in those scenarios. And its speed is another critical point. I've shown a lot of pictures with different amounts of sea level rise that could be locked in, that could happen in 200 years or 1,000 years. We don't have a good resolution on exactly how long it would take. It's easier to project the amount. Like if I dumped a big pile of ice on this stage right now, we'd all know it would melt, but it would be much harder to tell you how many liters per hour and exactly when would it finish. And that's the job that most sea level rise projecting tries to do, decade by decade. And ultimately, the speed of that change is what's going to be critical. Just like it's the speed of a bullet that makes it dangerous, not the bullet itself, not if it were just in my hand or thrown. So that's the story. You can explore all of these resources via picturingourfuture.com. And I'd be happy to take any, actually also .com, but .org. We are at .org. We also bought the .com. I'd be happy to take any questions. And I think we also have the possibility, if people want to ask to see any particular geography or any particular scenario, those folks can stick around and we can do that. We can explore the map a little interactively. So thank you for your time and attention. Any questions?
Will you join me just saying thanks to both speakers? And we now want to ask if there's any questions either online or on the floor. So I'm quite happy to kick things off with a question because one thing I was really quite interested in, having heard your talk, was about your machine, and this might be something you want to discuss later actually, but about your machine learning algorithm. I was wondering how it coped with the coast of Finland, where there's ice coming off the coast and the land might be rising because of that. If you see rises in elevation, and if you could just maybe talk about that slightly.
It's a great question about the elevation data, asking specifically about Finland, where land is rising because of the unloading of ice. And the truth is that Finland is not the only place in the world where there is vertical motion of the land. There are many places where the land is sinking at different rates, or in fewer places it's rising. And these elevation data do not take that into account. They are based on a snapshot in time, or maybe two snapshots in time, but they basically capture, they're based on data that was collected between 2000 and 2020. Some of the key data is 2000, but some other very key data is 2020. What does take into account vertical land motion, however, is our sea level projections. So when we do the map to show water, above or below the land, and we're showing a particular scenario, we put in the local projection. We basically incorporate the local projection for how much the absolute elevation of the water rises, but we also factor in anything we know about the absolute elevation of the land changing because of sinking or rising. And we basically take that difference. So in effect, we are incorporating the vertical land motion that we know about, even though it's not in the elevation data themselves. Yeah.
That's fantastic. Does anyone else have a question in the room? Do you want to come up and ask it?
So just wanted to ask if you would be able to show us what will happen to the Pacific Islands and when it comes to sea level rise, and how much time we've got to help them.
So the question is about the Pacific Islands. Is there, think if there's one you want to look at. Let's try typing into the map, into the search, Kiribati, which is spelled Kiribati. And I want to start with Kiribati because I years ago had the opportunity to meet the then president of Kiribati, Anote Tong. Now you're going to have to zoom in. Let's zoom in to, you're going to have to zoom in a lot. Or maybe zoom out and come back to a name, maybe try Tokelau, which is close by. It's hard, there's so much more water than land. I've been reading about how since the last ice age, yeah, there we go. Okay. So, well, that's actually more encouraging than I thought it would be. That there is, an arc of land that's not even affected at 2 degrees here. It might be a little. It's in this particular color scheme. There's a kind of a light blue-green there, which is land. So there is an enormous loss of land at 1.5. If you change from full road map to satellite map style, you'll see that a little bit more clearly. The purple is land today, and the yellow is also land today. And then you can see the higher parts of the area there. Let's look at the Marshall Islands. Anyway, the president of Kiribati, I was around a campfire, just him and me and one other guy, and he said, "How long do we have?" And he said that he's asked that question to many different climate scientists, and they never answered him, and I couldn't answer him either. But imagine being in that position, like having to think about your whole country and having this deep uncertainty around how long it would be viable to remain there. I think, so 20,000 years ago, sea levels were 400 feet lower than they are today. The sea level rise, fortunately, well, there's only 200 more feet the sea levels could rise with the ice that's left. There was a lot more ice on land 20,000 years ago. And most of the melting and the sea level rise happened between 15,000 and 5,000 years ago, through natural climate change. And in Southeast Asia, let's try and zoom in to the Marshall Islands. In Southeast Asia, there's a whole landmass between today's Southeast Asia and Indonesia. Indonesia was connected to Southeast Asia, and so were the Philippines. And an area the size of India was lost below the water. And there's a great deal of evidence to suggest that the ancestors of Pacific Islanders came from that land. They got in their boats, and they were, in a way, victims of sea level rise 10,000 years ago, but became a seafaring people, the most skilled seafaring people. And it's tragic that after that experience 10,000 years ago, now this danger is coming again to the place that they found, where they found sanctuary. I think we have to zoom in more first. I don't know which atoll is, but yeah, it's all just purple. There's a few yellow dots, but like everything is below 1.5 C here. Let's try switching the map, choose map, and just go to year. So, and let's go from satellite back to the full map in the upper right. So again, pretty much everything prone to annual flooding by mid-century. If we get rid of the annual flood level, and change other settings, and move this just to sea level rise alone. Yeah, it's hard to get that to look any good at all. So you'll understand why the Marshall Islands has been taking such a vocal and important role in trying to lead toward more ambition. Any other questions or places that people want to look? Oh yeah, we will be at the AO Pavilion showing a lot more from the Pacific Islands and other islands on Friday at 2 o'clock. So Friday at 2 o'clock, similar presentation, except really more focused on this century and Pacific Islands and other small island states. Yeah.
So just wanted to suggest that we look into a country that's much closer to us, the Netherlands. Despite of their flood defenses, what will happen to them if sea level rises? Exactly.
So if we could go to the Netherlands. So the Netherlands is tricky for us to show that in our modeling, we have detailed data on where levees are in the United States, but we have not identified a global data set that I don't believe it exists that shows where levees are or how high they are. So the Netherlands looks much worse than it is because it's very well defended to a high engineering standard. What I can say, let's just switch it though and choose map and go back to warming choices. And the kind of sea levels that we're talking about here with warming choices are, multiple meters. And even at 1.5, where it's something like 1.5 degrees Celsius, it's on the order of 3+ meters, if I remember. I was once at a conference with one of the leading water engineers from the Netherlands, and they're probably the best water engineers in the world. And he led one of the big companies. And he said, you know, I think 1 meter of sea level rise is a very interesting challenge, right? Like, he had a lot of ideas about what the Netherlands could do with 1 meter of sea level rise. But he said, 2 meters of sea level rise, that's not really interesting to me or to any other engineer. It's really just interesting to the prime minister, who would have to knock on Germany's door and ask if there were room. So that was the perspective of, you know, a top engineer from the Netherlands. Remarkably, there's been almost no research on adaptation to these more extreme sea levels. All of the adaptation literature stops in 2100. It stops at 1 meter, maybe 2. There was one project, I think called the Atlantis Project, that imagined 5 meters of sea level rise. And all they did was they gathered a bunch of experts to talk about it in a bit of a structured way. And they concluded that basically the Netherlands would be abandoned. Although it was, in fairness, it was 5 meters of sea level rise within about 150 years. So if it took much longer time, maybe there would be a way to work it out, you know. But maybe it would become a floating nation in a great lagoon. It's hard to know. Other questions or places?
Do you want to come up here to ask the question? Sorry.
I could have just said it probably. Does this tool look at rivers, lakes, freshwater, or is it just the sea level rise?
Right now, it's looking just at sea level rise.
What was the figure that you said as far as the amount of ice and what the maximum sea level rise could be?
Oh, you know, all the ice in the world right now would be about 200 feet or 60 meters.
Okay, from now.
From now. But most of that is pretty well locked up in Antarctica. Like, there's plenty enough scary sea level rise that's available to happen quickly, you know, from the fringes of Antarctica and Greenland. But when you get, you know, so we could see 10 meters, we could see 20 meters. But to get to the second half, the last 30 meters, or then you have to get into the interior of Antarctica and it has to melt. Like, it's not attached to the ocean in the same way. So that's a whole other level of a cataclysm. We will have many bigger things to worry about before we get close to that.
Thank you.
Yeah.
Are there any other questions from the floor? So in that case, I think I'd like to thank both speakers again. And I'd also like to invite all of you to our next event, which I believe is at 6 o'clock. Thank you very much.
Thanks for the time. Thanks so much for having us.